So I'm actually kind of glad that in my previous video I specifically explained that I cannot stick to any tight schedules. And I guess I was right, because, well, this took a long time to record. It's not that it took a long time, it's just that the delay between the videos were pretty long. Anyway, a sum is a finite summation of the harmonic numbers. Now, I've actually done a video before about this, but it's not anything like this. Before, it was me explaining how this thing diverges to infinity. And exactly that reason, the top bound is not infinity, it's actually n, because otherwise it'll just infinity. And that's pretty much it. Okay, so, first off, because this sort of operation, we don't really know about it yet. It's not like sine or cosine where you can transform it into any other function. So here's what we're going to do. Once again, the harmonic numbers is just 1 plus 1/2 plus, and then dot 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 to 1 over n. So what we're going to do, we're going to write the k equals 1 case, which is 1. The k equals a 2 case, 1 plus 1/2. And we're going to write it in these sort of columns over here. So we have rows, like we did before. And then plus 1 plus a third plus dot dot dot. And then it's just going to... Oh, wait. That's not what I meant to do. 1 plus 1/2 plus a 1/3 plus, and then dot dot dot, all the way up to 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over n. So this is what our series looks like. Now, because before we were talking about it in these rows, so basically this is the first term, this is the second one, this third. Now I'm going to look at it in columns. So the columns here, for the first column, it's just a line of ones. The second column, a line of 1/2, all the way up to the nth column, which is just going to be, well, there's only going to be 1 over n. So we can write it this way. We can write it, because obviously this is going to be 1, 2, 3, so if it's the nth column, there's going to be n columns. So basically we have n ones, and then this one, if you add a 1/2, there's going to be another column, but it's not, so it's going to be n minus 1 times 1/2 plus, do the same thing, n minus 2 times 1/3 plus dot, all the way up to plus just 1 times 1 over n. Now we are going to write it in a better way, pretty much. We're writing in summation notation, I mean. K, you're starting from, let K be the denominator of this, because it's 1 to n. So basically it starts from 1 and then it ends at n. Now, first of all, the denominator is k, of course. There's nothing wrong about that. When k equals to 1, this is going to be n. When k equals to 2, this is n minus 1, and just keeps subtracting 1 each time. But it's not k minus n, because if k equals to 1 here, this should be n minus 1, and this is n. So we're going to have to do, first of all, subtract k, and then we're going to have to add 1 to it. And then this is our change series. And this is quite a bit easier to solve. So first of all, we're going to separate this, because basically we can write it as n plus 1 minus k. So if you partition the fraction into the n plus 1 over k and negative k over k, we can get two different sums. Now, for the first one, n plus 1 over k, n plus 1 is a constant because our summation is with respect to k, so we have n minus 1 up, n plus 1 at the front, and then it's just times 1 over k, and there's the sum of that, which we define as hn, which is the harmonic number n. And then for the minus k term, first of all, it's going to be minus. Now, from 1 to n, there are n numbers, basically. So if n equals 3, there's going to be 3 numbers, 1, 2, and 3. So basically, there are n k over k's, which is n ones, so minus n. And that's it. That is the sum of this one. Now, now, I want to slightly change this up a bit. I want to make it slightly more complicated, but it's somehow still doable in this fashion that we've done before. So, this is going to be our first sum, and then I'm going to erase it, and I'm going to write down the second one. It's still going to be a sum. It's still going to be a finite sum from 1 to n, and we're still going to generalize it using our previously defined path, you could say. So hk, but this time we're going to divide that by k. So the same thing as before. We're going to write it in these row-column forms, almost like a triangle. Maybe we should call it the triangle forms, I guess. So when k equals to 1, it's just 1 times 1. When k equals 2, it's going to be 1/2 times 1 plus 1/2. And then plus, and then dot dot dot, all the way up to 1 over n times, well, 1 plus 1/2 plus dot 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 plus 1 over n. Now we're going to just multiply it out, basically. We get 1 plus 1/2 plus 1/2 times 1/2, 1/4 plus 1/3 plus 1/3 times 1/2, basically. That would be 1 over 6 plus 1 over 9 plus, and then dot 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 plus, and then it's going to be 1 over n plus 1 over 2n plus dot 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 plus n squared. Following the pattern, because 1 for 9 is going to be the squares. So this is going to be our new series which we are going to work with. And like before, we are going to look at it in these columns, right? So for the first column, 1 plus 1/2 plus 1/3 plus 1 over n, that is just the harmonic numbers. So for the first row, first column, it's going to be the hn of n, basically. Now the second one. The second one has the same sort of pattern, but its increment is 2 each time, and it starts at 4. So we can factor out a 2 out of all of this. We have plus, well, for plus of course, and then we have 1/2 times 1/2 plus 1/3 plus all the way up to 1 over n. Now, say we're going to add a 1/2 to this. If we add a 1/2 to this column would just be the harmonic numbers. But obviously, we have to subtract that one, otherwise we're just going to change the value. So we're still going to have a hn over here. But this time we're going to subtract 1. And here I'm going to write 1 as h1. This is so it's simpler later. And then plus 1/3. Same thing. And we look over here at the columns. So it's going to be 1 over 9 plus 1 over 12. That would be, would that be 12? Yeah, that would be 12. All the way up to 1 over 3n. Now, let's say we add 2 terms here, which is going to be 1/6 and 1/3. If we're going to add those 2 terms, then this column will just be 1/3 times the harmonic number of n. But obviously, we're going to have to subtract these 2 terms, these 2 imaginary terms. And so, you know, that hn minus, this is going to be 1/3 and 1/6. But we have already factored out a 1/3, so this is going to be 1 and 1/2, which is going to be h2 plus da da da. All the way up to basically the last column, which is going to be, I'm actually going to write it in slightly a different fashion. 1 over n, obviously, and then we have hn. So basically what we're saying is we're adding up 1 over n times n minus 1, n times n minus 2, all the way up to 1 over n times n. And then we're going to subtract those terms. So minus, this is now going to be the harmonic series ending at n minus 1. So this is our new sum notation. Now, like earlier, we're going to rewrite this using summation notation. K is equal to 1, 1/2, 1/3, so k is going to be the denominator of these fractions. So it's going to start from 1 and then end with n. So obviously there's going to be a k in the denominator. We figured that out. And this k looks more like an h, so I'm going to have to rewrite it. So we have a k in the denominator. why does that still look like an h? I'm just going to let it be. Now, at the top, we are going to have an hn here, obviously. And then it's going to be minus, because here, technically it should be minus h0. Now, is h0 0? So, if we're going to look at the harmonic series, it's going to be like it's going to be hn, it's going to be 1 plus a half plus a third all the way up to 1 over n. Now, if we were to subtract this from this, well, we would just get 1 over n. So now, what we're going to do is we're going to set n to be 1. So basically, we're saying h1, 1, we know that's 1, minus h0 equals 1. And solving for h0, we have h0 equals 0. So this thing can be expressed as h0. Now, if we're going to express this as h0, k would start at 1, and this would start at h0. So we're going to do hk minus 1. Now, we're just going to split it again. So first of all, we're going to do this part of the fraction. So ignore this. Hn is a constant because we're summing with respect to k. So we have hn. And then it's just 1 over k again. It's the sum of that. So we have hn again, which is going to be hn squared, basically. And then now, for this term, hk minus 1. Now, we have literally just said that hn minus 1 is equal to 1 over n. So now if we were to redo this, or basically we're going to undo this, that's not how you explain it. Basically what we're going to do is we're going to solve for hn minus 1 and replace n with k. So this is basically hn minus 1 over n, basically. So this is now subtracting the sum. K is going to be equal to 1 to infinity. God. No, messed that up. I got used to saying from 1 to infinity, but never mind. This is going to be hk minus 1 over k. Okay, so, first of all, if you ignore this, hey, that's just our original series. Now, I'm going to call this, I'm going to give this a name. So, hk denotes a sort of sum of fractions, and dividing by, there's k terms. So if you divide that by k, you get the average or the mean of the harmonics. So I'm going to name this, I'm going to define it as the harmonic mean sum of n. It's just a temporary name, I guess. So now we have, I think I'm going to have to space this out a little bit better. Hn squared minus. So hk over k, that's just the h s o n. Now, minus, that's going to be a plus. And now, if that's going to be a plus, it's going to be plus the sum of 1 over k squared. Now, this is something that is called a generalized, I think it's called a generalized harmonic number. And it's going to be defined slightly differently. So, we're going to have to define it hn of the mth degree being defined as the sum. First of all, there's some variable k equals 1 to infinity, 1 to n, 1 over k to the n power. Now, we have literally just defined this. So, now, if we're going to write it using this notation, it's going to be minus 1, this is going to be plus 1 over k squared, and it's the sum of that. So we have hn of the second degree, and this is it. Now, what we're going to do, so we're saying that this is equal to that. Now, if we were to add the harmonic mean sum on both sides, we get 2 times this equals this plus this. And so we have, well, 1 3 divided by 2, we have our final solution, which is that our sum, maybe I'll write it here, which is that our sum, k is going to be equal to 1 to n of hk over k is going to be equal to hn plus hn of the second degree, hn squared plus hn second degree over 2. This is pretty much it. This is the answer. It's pretty interesting, actually. And we actually used... Did we use previous knowledge? I don't think we used previous knowledge. So these are two completely different sums. Anyway. If you look at this expression, you may consider to generalize this, because you see 2, 2, and 2. But so far I found no generalization with hn to the nth power plus hn to the nth degree over n. So maybe that's going to be a task, but so far I haven't been able to do anything similar. So this is it. This is going to be 2 harmonic sums, and a video that is horribly out of date, out of schedule. Well, there you go. Better late than ever, or whatever the saying is. So I'll see you guys whenever I upload next, even though it's probably going to be a couple months from now. I'll see you there.